The factored form of the polynomial functions are the forms that have factors, obviously, and factors are just things that get multiplied together. So in this example, I have a. A just represents a number. It's the value of the leading coefficient. And then our factors are x take away r, x take away s, x take away t, and so on, depending on what degree of a polynomial we have. The factored form is good because it tells us our x-intercepts. From that, from that factored form, we can also determine the degree and the end behaviors for that polynomial. So I'm going to give you an example here and we'll work with that. All right, so our example has a positive 3 in front here, and that positive 3 is multiplying all of these factors together, and in these factors we have an x times an x, which would produce an x squared. This factor has an order of 2 up here, so that means it will be an x squared when we expand and simplify that. So x squared times another x squared would be x to the 4. And then because this one has an order of 3, I would get an x cubed out of this, and x to the 4 from the previous stuff times an x cubed would give us actually a degree of 7 for this polynomial. So 7 is an odd number. It means my end behaviors have to be opposites, because odd, I'm thinking linear relationships. They're either going to go up to the right or up to the left. Now, because my leading coefficient happens to be a positive value, I think of as a line with a positive slope. So my end behaviors would go that direction. So I know that the end behaviors go from Q3, quadrant 3, and head upwards towards quadrant 1. So Q3 to quadrant 1, remember you're listing those in order from left to right. Now, the factored form also tells us our x-intercepts. So from this very first one, x minus 2 would equal 0, which means x equals positive 2. X plus 1 equals 0, which means x equals negative 1. X minus 4 equals 0, which means x equals 4. And x minus 5 equals 0, so x equals 5. Now, because the first two zeros here and here are order 1, their exponents are 1 up here. When I sketch this out, I'm going to have those zeros, or the graph just passing through the x-axis at those values. At x equals 4, we're going to get a bounce because its order was 2. It's going to bounce off of the x-axis, and an order of 3 here tells us we're going to twist at this particular x-intercept. We're going to pass through, but it's going to have that little curve there. So we could actually do a little sketch of that function by plotting my zeros and looking at the end behaviors and how the zeros affect, or the order of the zeros affect the graph. All right, so I've got my x and y axes drawn there, and I've shown my x-intercepts at negative 1, at 2, at 4, and at 5. And then I know that I'm going from quadrant 3. At negative 1, I'm cutting through. I could expand and simplify this to figure out my y-intercept, or just sub-zero in for the x and solve for the y. At 2, we're just going to cut through, so I could figure out that y-intercept. I'm not going to take the time to do that right at this moment. At 4, we're going to bounce off the x-axis, and at 5, we're going to do the twist. There we go. And then we're heading up to positive infinity there. So our graph could be sketched something like that. So factored form is good for that particular information. So if you need to make a note about when you get bounces, when you get twists, anytime you have an even order, you're going to get a bounce. If you have an odd order that's greater than 1, like a 3, a 5, a 7, and so on, you get twists. They just become more exaggerated with the higher order. Okay, so now the next thing you need to make sure you know is that you need to be able to get the equation of a polynomial function in its factored form if you know the zeros and another point on the curve. So if you had a graph, like I've just drawn a graph, you could use your x-intercepts to work backwards. So you know, for example, that your factors would have to be an x plus 1 to get that x-intercept there. We would have to have an x minus 2. And we would also probably need to know what order or what degree or the maximum degree of our function is, so that we know if we have that bounce at positive 4. To get a bounce, you have to have at least a 2 there. It could be a 4, it could be a 6, and so on. But based on that and what the question says about the overall degree of the polynomial, you'll be able to decide what order goes there. And then we also had the twist at x equals 5. So x minus 5 is the factor. To get a twist, we have to have a minimum of 3 as our order on that. Now we would just put a letter A in front and call that f at x if we're working backwards. And then what we would do is we would need one other point that's on the curve that we would sub in for x and the y to get the equation, to solve for the actual value of a in that equation. All right, so if you want to make a little notes on your summary sheet about how to get the equation from a graph or from just the zeros and a second point, this would be a good place to do that. Okay, so I have a quick little summary. Whoops. That's not what I intended to do. I intended to scroll this up, but apparently I can't. That's weird. They're two separate things. Anyway, I've tried to summarize what I had in here. Let me see if I can double tap. Maybe I can do this, select all, and I'm going to go copy, and I'll just do this. When in doubt, add it to the next screen. There we go. Okay, problem solved. So those are our quick steps there for doing that. Now the other key point, you've got application questions, which I can't really do a lot for summarizing. I'm going to let you figure that summary out for yourself, put down what you need to do for that. But I do want to talk or put a little thing in here about finite differences. Okay, so finite differences just tells you from a table of values, if you take your differences of your y, whichever difference is constant will be the degree of the polynomial. So if you do your differences in the y's and they're all constant, it's a degree 1, it's a linear relationship. If you do the differences of the differences and get a constant, the second differences are constants, it's quadratic. If you have to do the difference 4 times, then it's going to be a degree of 4 or a quartic relationship. So that's what you need to know for that part. All right, so for example, if the 4 differences are constant, it will be degree 4 or a quartic. Now that constant difference value is always equal to a, which is your leading coefficient, times n factorial, which is your degree. So if we have f at x being 7x to the 4 minus 2x cubed plus 5x minus 1, we know that function has a degree of 4. So that means n equals 4. And we also know that the a value, the leading coefficient, is 7. So our constant difference would be equal to a, which is 7, times 4 factorial. Now, factorial, from our video, remember factorial just means the number times itself, or times the numbers before it, till you get down to 1. So 7 times 4 factorial would be 4 times 3 times 2 times 1. And then you just multiply all that together. So the fourth differences will be constant, and they will have a value of 168 if I've done my calculations correctly there. All right, so that's a little summary on our finite differences. You still have your application questions that you need to know how to work with and be able to solve, but that wraps it up for our third unit.